Well, welcome everyone. So today we're going to talk about the possibility of constructing an operating system in a safe programming language. So it sounds a little unusual, but it's actually pretty cool. So let's take it step by step. So I'll just scroll. Again, we talked about, for the last couple of weeks, we talked a bunch about the fact that, monolithic kernels are bad, right? So you may have large, giant Linux like operating systems. Let me just enable some kind of annotation here. Where does it go? This one maybe? And maybe something like this. So 27 million lines of code, not fun. A bug in any of the subsystems essentially allows the attackers to propagate throughout the system by, just literally just discovering one right primitive, right? And so essentially we said, okay, isolation is a great idea. We should ideally try to run those individual subsystems in isolation. And that's what we were discussing last time, was this line of work, which I did on lightweight execution domains, lightweight VM-func domains, and then case split static analysis, which essentially takes like the job of heavy lifting, and essentially if there is a bunch of dependencies, it generates enough glue code around this driver that we can actually run it in isolation, right? So it was pretty cool, but still, like, there is a question. And okay, like we know that it's cool, like final Mautic report, which I keep bringing up, said that okay, it will improve security and reliability of the system if you split it, if you move for non-critical functionality in outside of the kernel into some kind of isolated subsystems. The question remains, why do we run monolithic systems, right? And by now, I assume that it kind of like it is kind of natural to you, meaning that, we know that overheads of breaking the system apart are kind of hard, right? So despite the fact that we have case split, which kind of automates decomposition effort, it's still like the system, like the isolated or decomposed kernel never runs really as fast as monolithic one. And here's a couple of numbers, like really what I want to say here is that in the past I mentioned that there are three major lines of work which try to implement isolation, right? So the first one is the more or less intuitive. It's hardware isolation primitives. We just say, look, we're going to use whatever the CPU provides, some kind of segmentation or page tables or novel hardware isolation mechanisms like MPK or MTE, stuff like that. The second line of work was the software fault isolation, right? And we discussed last time this work from MIT, which is called Alexafy. And it's fine, right? Like as we agreed, it's like almost matches performance in terms of throughput of the original system, but at the cost of like twice as high CPU utilization. And it's on a very wimpy 1 gigabit per second link network interface. So if you have something like a 10 Gbps link, then most likely it will be much harder to match the performance because the CPU will be saturated, and like essentially you will see the performance drop. And essentially we talked about this one. This is like LXDs. My work on LXDs I cannot write here as the right LVDs. And I'm by far not unique. Like I used my work to illustrate this line of research, but really there are like dozens of those papers. For each hardware isolation mechanism, like Intel MPK, you'll find multiple papers which try to bring isolation. Many of them, or not many, but some of them will try to bring it into the kernel as well, right? So it's kind of like the whole agenda, which just does this research, where people like essentially like use hardware isolation primitives. Software fault isolation, which again, in case of Alexafy, was a whole separate line of like it's essentially SFI was used as a standalone mechanism. Today, probably SFI will be combined with something like, again, maybe ARM memory tagging extensions, MT. We discussed it, right? So because you need I cannot write it. we need a sort of SFI pass to make sure that we control the value of the tag on every memory access, right? And however, today we're going to talk about this third line of research, which tries to say that we don't really need the first two, but instead we will implement isolation through a language safety, through a programming language safety, right? So you probably know safe programming languages like Java, C#, whatnot, Python as well, but it's interpreted so hex low. And today, the most practical language is Rust, actually, surprisingly. And it turns out that this language safety is a very capable mechanism to some degree. So essentially, you can kind of guess that, first of all, if in the past isolation was expensive because it required, not isolation, language safety was expensive because it required typically managed runtime and a garbage collector. Today, in case of Rust, it can be implemented statically at compile time, which allows Rust to be as fast as C, right? Or almost as fast. We'll take a look later today. So, okay, so let's take a look. So again, some numbers on isolation mechanisms, right? So we can probably skip those. Let's just go straight to the language safety, right? So this figure comes from a paper which was published in 2019. And what the paper is doing is they implement a very simple DPDK style kind of data plane development kit device driver for 40 Gbps. It says 10 Gbps, but I think it actually a 40 Gbps network interface, right? It implements the device driver in 10 different programming languages, starting from C, going to some exotic languages like OCaml and Python, but essentially they do everything. They do Rust, Haskell, Go, Swift, C#, JavaScript, Java. And the device driver is very, very fast. So let me show you a diagram. So it runs as a user process, meaning that the kernel is not involved at all. But there is a mechanism which we will discuss in a week after the Thanksgiving, so next week, which is called kernel bypass, which allows the device driver, which runs in a user process here, this P1. I apologize for the write-up. So this slide deck is done in LaTeX, so that's why I'm not using Word, and the markup is slightly different. And it turns out that, like, really you can, that's the fastest way to build anything, to be honest. Like it wasn't really clear, and I will talk about it when we get back after the break, but essentially this is a blazingly fast device driver. It's as fast as a kit can get. So DPDK is a commercial, it's called a network processing framework, but really it's a collection of device drivers and other functions which allow you to build some network packet processing workflows. Essentially, you receive a packet on a network interface, you do something like maybe you just pick a path, routing path, and then just you send it out or forward the packet either through the same network interface or maybe through a different one. It doesn't really, like, it's not that important, right? And what's important here in this wonderful diagram, and like, go to like, maybe selection will disappear. No, selection doesn't disappear. The observation here is that in the past, those programming languages, like even the fastest ones, which are like C#, with this orange line, were introducing significant overhead compared to C. So C is this black line, and the higher is the better. So it's a throughput in millions of packets per second. And this essentially a batch size. So you can send either one packet to the network interface, you can send a batch of 2, or go to a batch of 16, 32, and so on up to 256. Intuitively, the higher, the bigger the batch, the faster the system is going. But there are some equations which essentially say that, look, guys, if you batch the packets, then the latency for individual packets is going up. So for some workloads, it will increase the tail latency, which is not okay, right? So ideally, you should really stay within the limits of some realistic batch sizes, unless you know that it doesn't really matter that you can send like a giant batch of packets. And so what I'm saying on realistic batches of like 8 and 16, those languages, like even the fastest, like Go and C Sharp, Go is a green line, C Sharp is an orange, it reduced significant overhead, like 42% slower, 36% slower on a batch of 16. So in the past, despite the fact that those languages are hell fast, right, or considered to be the fast, safe programming languages, C is still much faster. But what has changed is there's this beauty of Rust. So Rust is this blue line. And even on realistic packet sizes, it introduces kind of like, you can say significant, but not horrible overhead. It's 10% here on a batch size of 8 packets and 8% here in a batch size of 16, right? So, which means like, it's an area of research. And remember, I was even suggesting to do a project on this to kind of investigate what really brings this overhead. So kind of take a look at the Rust code and see what really makes it slow down. Like, is it like the number of instruction which the compiler generates, or higher level language features like, like option types or something like that. And in practice, everything, like all of it, just all these individual bits, they do slow you down. Like Rust generates on average almost twice as many instructions. Like that's what, again, the people from this paper and my own research kind of like shows that really like the CPU is actually quite amazing, that you generate twice as many instructions, but still you only run 10% slower, which is pretty amazing, right? But so the high level observation here is that Rust is becoming a really practical systems programming language, just because the overhead is getting close to C. And I will show you later today in this lecture, or if I run out of time in person on Monday, that if you write very careful Rust, and specifically C-like Rust, then the overheads are literally like almost approaching 0% on certain workloads. If you start using higher level language constructs, then overheads go up slightly. Okay, I'm not exactly, again, sure how much background you have in Rust, so I will give you like a very tiny, like a 2-second introduction, like to Rust. Again, kind of, I apologize, I don't think I can give you a 2-second introduction to Rust. I'll give you the main idea behind what makes Rust fast or practical, right? So in a in the past, in most typical practical safe programming languages, and just to reiterate, you remember what safety means, right? So C is unsafe language, Java and C# are safe. So it's like if you have a pointer or anything, right? So if you looking at the object on a heap, there are like 3 major things. So first of all, you use it correctly according to the type. It's called the type safety, right? You use it according to the like size, so essentially spatial safety. So if it's an array, then like really you're not going to do it an out of bounds access. So, but like if P is a object of type, if a pointer to a type A, then this, like, the language guarantees that whatever you have on a heap is type A, right? So it's type safety, spatial safety. If I can write in cursive, then I know it's a little easier. And finally, it's temporal safety, meaning that for as long as the pointer is valid or used anywhere in a program, the object will exist on a heap, right? So it means it will not like be deallocated, right? So by the like some kind of a free operator or something like that. And that's essentially temporal safety. So there's 3 things. I haven't written in cursive in a while. Okay, so how do we typically implement those 3 things? In a language like Java, so for example, if you have a function, or we can call, say, a scope of execution, like something what runs between the braces, right? And you allocate a new object on a heap, so like kind of like a vector here. Okay, cool. You allocated it and you have a variable which points to that vector. In Java, you can freely pass this pointer anywhere, like to another scope of execution, right? So essentially, Maybe it's a nested scope when maybe you invoked a different function, maybe even somehow you passed it through a communication mechanism and actually it's running in a different thread, right? In Java, of course, if you deallocate, like if you essentially A goes out of scope, and then later B goes out of scope, right? So at some point you ask yourself a question, is it safe to destroy this object on a heap, right? Because remember, in Java, any number of references is possible. And the problem here is that you don't really know the answer to this question, right? So you really need to run garbage collector, and like which scans the entire heap and essentially figures out that nowhere like in the program, like nowhere in a stack, nowhere in a heap, nowhere in global variables exists the pointer to this vector. At this point, and that's like it's a garbage collector scan. At this point, you say, look, it's free to deallocate. At this point, you deallocate the vector. Running garbage collector is expensive. Ironically, however, it's not just one overhead. I simplified and reduce everything to a garbage collector, but there are some additional overheads here, so I don't want to go into those. But in Rust, how we implement safety, remember spatial and type, those you can do like at compile time. The question is like, how does Rust implement temporal safety? So what it does is that it makes a rules so that if you have a scope of execution and you allocate something on a heap, right? You have a owner, which kind of like owns the variable on a heap. And if you suddenly pass this pointer into another scope of execution, this reference is moved, meaning that A cannot retain a reference like this. So this is not allowed, right, in Rust. And if you try to like dereference the vector through A, the compiler just says, okay, it's an error. I cannot compile this code because, there is a bug. And of course, it's called single ownership, right? And it's kind of beautiful because you know that when B will go out of scope, at this point, it is safe to deallocate the object from the heap, right? Because you know that there will be no other references into this object, right? So that's essentially this idea that you don't need garbage collector to essentially reason about lifetime of objects, right? And it's kind of powerful. Like, in fact, this ownership discipline, or this, sometimes it's called linear type system, because linear type systems allow the use of variables some number of times. They kind of restrict what can be done with pointers, right? And it has kind of like interesting consequences. So you will see one consequence here in this lecture, but another consequence that it also like allows you to build mathematical proofs of correctness about your code much easier and much faster, just because instead of like reasoning about every pointer and like, what if it points anywhere in a heap? Like, how do we know that it points to a specific variable? Maybe it points to object A, or maybe to object B, or maybe somewhere else. So it gets a little bit complicated. People do it, right? But it gets like it requires a lot of effort. But in Rust, this discipline of single ownership essentially takes care of it and actually simplifies construction of those mathematical proofs, or as people say, formal verification of a program, right? Okay, but okay, for now, just done with this short primer on Rust. That's essentially what we cared about, is that Rust is a safe language, doesn't need garbage collector. And the beauty of it is that in many cases, if you take the Rust code, if you take two pieces of code, Rust and C, and if, for example, iterate a loop inside the array, it will compile to almost identical assembly. And that's beautiful because you can actually reason about it. Like you can, as a human, as a system developer, you can take a look at the assembly and say, look, I understand what's going on. What it really means, it also brings something what we can call a performance transparency, meaning that, well, if I take a look at Java code and you ask a question like, okay, can you guess how many cycles a specific thing will take? I'm confused. I don't know. I really have to understand what Java does underneath. Same in C#. But in Rust, it's much easier. So like, of course, Rust can do something like if you have some option type or some kind of a wrapper type around something, right? then you have to understand like how many dereferences will happen here, what else is going on, are we acquiring any logs or anything like that. But nevertheless, this kind of leap towards understanding what's going on inside is much easier, right? And in Rust, almost like in C, you can take a look at the C code and reason about its performance, right? So it's not a super hard skill. Same in Rust. So that's beautiful. So Rust essentially is a beautiful language this way. And it has this powerful consequence, right? So we talked a lot about it, right, in the past. Maybe I even showed this plot from presentation by Microsoft Research, which essentially says, okay, we take all the vulnerabilities in the systems, low-level systems code in Microsoft, and those are like stack corruption, meaning that's like stack overflow, heap corruption, out of bounds access and stuff like that, use after free, type confusion, unsafe typecast, and you say, look, you treat a pointer to A as a pointer to B. Uninitialized use of a variable. Remember, we had this category like forgot to initialize, A is not 0, and everything goes to hell. Or even like heap out of bound read and other we'll talk a little bit in a second. So if you take a look how this vulnerabilities, the classes of those vulnerabilities evolved over years. In 2006, we had a fair amount of like stack overflow vulnerabilities, this blue category, right? So, but then probably they implemented some kind of a stack canary discipline, settle stack. Right now we have almost 0, right? Like some single digits, similar to heap corruption. So they did something, but didn't fully eliminate them. Used them for free, kind of a large category here, so kind of like still smaller here. But what's important is that all of these vulnerabilities, which kind of like related to like low level unsafe features of the language, roughly speaking, there are like 70% of them if you count like the top number. The total is, what is it? And there is other. So this 70% of those low-level safety-related vulnerabilities arguably can be eliminated by Rust. So if you rewrite your code in Rust, other will stay because other cannot be fixed by Rust. Maybe it's a logical error. You do A versus B, and you cannot, like, the list is not sorted in the end, right? But obviously, other classes of vulnerabilities will disappear, right? That's great. So Rust can get your programs like your systems. If you simply rewrite your kernel in Rust, it will like have 70% less vulnerabilities, but still will have this 30 others, right? But anyway, but what I'm talking today about is not just Rust and the idea that you can take a Linux kernel and rewrite in Rust. I'm asking a question, basically, can you write an operating system which has familiar abstractions of like processes, and maybe a microkernel or a kernel, I don't know, whatever you want to call it. This is a kernel, right? And instead of using any kind of hardware isolation mechanism, like, sorry for this, hard or software fault isolation mechanism, can you use just a programming language to make sure that this isolation creates process-like isolation between the code which you execute? It feels a little bit unusual, right? As I mentioned in the beginning, so because you say, look, how can we even do that? The language is just calling functions. What do you mean? Like, how do we build processes with the language? So that's essentially what I'm trying to explain here. It gets a little bit involved. So let me take a detour. To take a detour, I really need to like have a better, slightly better drawing software. Like, let's use it here. So in general, like imagine a high-level goal. You say, look, I have some collection of processes, kind of P1, P2, like P3, and I have a kernel. And everything is written in the safe language for a sec. We don't use any hardware isolation mechanism. just the idea is to show you how it can be done. And then from there, we will go into explaining how a real kernel can be constructed. And then from there, we can talk about, forgot my line, just let's stop here. Okay, imagine those processes, they exist, like imagine this is a shell. I don't know, this is WC. I don't know, this is cat, whatever, right? Like kind of like x86 style. The question is like, can we achieve isolation by just writing this all of it in the same language? Roughly speaking, I say yes. So meaning, let's imagine like for example, we have some kind of a main function in this kernel, and it has some kind of a like function which we wrote, which like does something like create process. And maybe it takes like an elf file as a argument, right? And returns, well, I don't know, like pointer to a process data structure, similar to how we do this in x86, right? So imagine for a sec, so we take this elf. Inside this elf itself, let's imagine it's a shell program, right? I'll just like make a line here. So it also will have a main function, right? And maybe it will take some arguments. Like, for example, maybe it will take something like syscalls. It's in Rust, it will be something like a trade, but imagine it's a collection of function pointers, right? And then later on, it just says, okay, I run it. So essentially, like I will execute like as something like a syscall for console read. And if we pass s, like when we do create a process, right? Imagine we're passing s as an argument into main. So then this s will exist in this process. S will essentially just allow us to call something like console read in the kernel. Agree with this? And well, why not? Like we did console read, like we read something from a console assigned to a variable, I don't know, C, did some parsing, and so on and so on. And another like as can be create a process which we like whatever put some pass, and then they like when we call this create process in a kernel, that will create something like WC, similar to how we did it here, right? It's everything is written as a program in a language, right? By the fact that we controlling what we are passing into this main of this shell, for example, we say, look, the only state of the kernel, this state, right, this heap of the kernel, which shell can access, is really can only be reached through this as variable. Maybe as has no public pointers. It only has function invocations like read, console read, create process, read a file, stuff like that. It means that we kind of have this idea of a process in a language, right? Why not? Because we said, okay, look, like this guy, no matter what it does internally, no matter what its main does, as long as it's all safe programming language, right? We know that it cannot access the state of the kernel. It can invoke functions of a kernel, but it cannot like really do anything funky and like override the state of the kernel. And it cannot like access state of other processes because, you know, like it just simply doesn't have any pointers to those, right? And like, okay, why not? Like if you take any safe programming language, be it Rust or Java or C Sharp, then that model will fry. So this is the kernel, and this is a shell. And of course, it would be nice to go into some kind of a discussion right now and like talk to you, ask your questions. But hopefully this idea looks at least plausible, right? So essentially, we control what we essentially are doing here is that we say, look, there is something in this like space of this program, which is a kernel, and there will be a space, like object space of a process, and we allow process to access something in a kernel, but in a very controlled manner through like as, and those are the syscalls. And through those syscalls, maybe like they take individual functions like read. This process can invoke, can do as read, and maybe pass a pointer to a buffer, which it has, and then the read internally in a kernel can write into this buffer, right? So that seems normal, like that's okay. That's what the real x86 kernel is doing. I said real, but just let's say unsafe kernel is doing. But really, like if there is some like read internally might have some private state, like as a collection of other objects within a kernel, like on a heap, right? And read internally can access those objects because maybe it has access to like some global variables in a kernel which allow it to like essentially access this object hierarchy heap of the kernel. But really, it cannot really, as long as the read is implemented correctly, it will never send any of these objects back to the process, right? And that's believable because there are type checks, stuff like that, right? So okay, there is a couple of interesting things which I kind of like glance over. I said first here that it's an ELF because you say, look, if you write everything in a single program, right, then you unavoidably end up with a very, very static system. So you can say, look, when the kernel is booting, it might have a list of possible programs which it can start. So it can start a shell, it can start a WC, it can start something like, I don't know, cat. And then, those are like known types and classes. And that's a little restrictive. So, but in a safe language, I mean, it's through an unsafe operation, which unsafe, I mean, like how to explain it. So every safe language is really two languages. A safe subset, like which follows the rules of the safety, like linear type system, for example, and unsafe. And unsafe is like C, like do whatever you want, right? And typically in Rust, it's like requires an explicit unsafe keyboard, and you encapsulate it's like this can do anything, like overwrite any state, right? But what I wanted to say is the following. So let me just actually delete this. What I wanted to say is that or just move this out of the way. Is that you obviously don't want this kind of like static nature of the system. You say, look, the kernel will, instead of having this list, you say the kernel will take any ELF file as long as it's compiled according to the specific ABI, so kind of like syscalls and like maybe some other arguments, but let's just for a second imagine it just takes one argument, syscalls. Like, what does it mean to compile an ELF? You just simply compile a program in Rust, package it, like it has to be a standalone program. Maybe it can rely on some libraries which our kernel will support, but like just for a second, imagine it's a standalone library, so it doesn't depend on like Linux syscalls or anything like that, right? And just packages as an ELF file, then obviously this kernel can implement an ELF loader. And we've seen ELF loaders like in the x86 kernel, but it's borderline trivial. So okay, you just read this thing in memory and then jump to the main function, right? And pass, as long as you have the ABI, if you know that this code, if this whatever you got inside this ELF expects the specific stack where the syscalls and other arguments will be packaged on a stack, then you find to invoke this ELF file, right? Of course, like this is how we essentially, like this safe kernel can load any piece of code, like then load anything from the internet. As long as you trust it, then just invoke it main function and go forward. Because the question is like, what if some attacker compiled this thing in C and it really just all unsafe here? And then it can like immediately override the kernel, right? So that's a little bit of an unsolved problem in those safe operating systems, meaning that you really have to make sure that whatever you're loading can be verified somehow. There are different mechanisms for how to do this. You can use something what is called proof carrying code or typed assembly language, where you can verify that even at the level of assembly, like or some assembly, you can say that it's actually like conforms to the rules of Rust safety, for example. no one actually can do it today. So this is unsolved. But, or alternatively, you can just say, look, whatever the code which you get is signed, and you get a signature, and you essentially trust the build environment. Like you have a farm of those trusted servers which build those programs and say, look, we know that you used Rust, we compiled it. There is also a way to check that there are no unsafe code. There is no unsafe code inside. Means then we will sign, and that means that the kernel just checks the signature and says, okay, yeah, it's safe to load, right? So more or less we understood how to load any programs, right, in memory in this safe operating system. And what the other thing which I wanted to make sure is clear, because you might think that, okay, look, I kind of get it, but I still don't get it. Like, how does it work? Like, imagine like process is running, like P1 is running. Imagine what happens to timers. So imagine you have a timer interrupt. Oops, sorry. What is this? It wasn't a timer. It was a lightning strike. So imagine you have a timer interrupt. Well, since we loaded the kernel, we control the interrupt descriptor table, IDT. That's what the hardware is using. Like inside the IDTR register, the hardware will point here, right? So it will deliver a timer interrupt to the handler in this kernel, which we have, which is implemented in, like, let's say Rust. Roughly speaking, it's not important. What's important is that this is implemented in Rust, all the processes. The kernel can be implemented in any language. Ours built in Rust, and we used some amount of unsafe code, right? But anyway, so you get the handler, and the handler says, okay, I got it. So it follows the same kind of rules of the hardware, right? It says, okay, I know that on my kernel stack, right? Kernel stack, you save the current state of whatever was running inside this process, like IP address, code segment, stack segment, stuff like that, right? You saved those 5 things here. And you ask yourself a question, how can I build a context switch? Well, similar to how you do it in x86, just like whatever, save this kernel stack as part of the process data structure, P1, and then essentially maintain a list of processes, kind of like a list which points like to P2, P3, so on. And you say whatever, like I assume that P2 was running in the past, it also has some kind of a kernel stack. And you just do a switch function and essentially start executing, and and that's essentially the context switch, right? So essentially you say switch is very similar to how you write it in assembly. You can also write it in assembly here. And essentially that, like, the context switch follows the rules. And those things are safe, right? So it's like all safe Rust, safe subset of Rust. The kernel itself is Rust, but with a lot of unsafe, or like some amount of unsafe. But essentially kind of everything works as similar as in x86. The only difference is that, like, we don't use protection rings. So everything can run, for example, in ring 0. Everything is running in ring 0. We never do a syscall here. We don't have to, because we don't need this isolation. We trust the safety of a programming language to make sure that when the call is done as what I was using, console read, it's like lands us on the S variable in a kernel. It will have a method console read, and so on and so on, right? So I hope you guys got it, right? Okay, hopefully this is clear, right? So if not, then please come talk to me. I will be in person Monday, so you can always ask a question and say, look, I can get it. Can you explain this safety thing again? But back to my slide deck, what I wanted to say, we kind of understood what this hardware, what the isolation means in the language, right? So essentially, you create typical data structures like you do normal, like you say, that's the data structure A, and it has some fields, and some fields are public, meaning that they can be accessible from all over the program. So if someone can essentially oh, it's not all over the program, you probably get the point. It's kind of like private and public variables, but you control what can be accessed where, and you control who can access which pointers and who can follow which pointers through those public and private fields and stuff like that. Okay, got it. So now the question is, how can we build something like usable or useful out of it? Because I was kind of simplifying a little bit, because I was saying that it's so easy, just call an S and pass a whatever console read, maybe pass a buffer. And that kind of like starts falling apart a little bit here, because like when I say pass a buffer, what does it mean? Like, am I passing like a complex data structure, like a linked list or maybe a tree across? And you have to be a little bit careful with if you want specific properties from this kernel. And so let's take a look here. So imagine we have like two isolated subsystems, if you like, two processes in this kernel. One is A, one is B. They have some private state, like, so one subsystem is blue, has state of like a bunch of objects. One subsystem, one heap is like, or object space, I guess. Like, let's not call it a heap. It's just like, maybe it's on one heap for now, but like it's just a collection of objects, right? And so here, for example, O1 is private to A, O5 is private to B. So B has access to O5 and obviously can reach O6 and O7. And similarly, A can access O1 and can reach other objects, like all of these objects recursively, because it can follow the pointers, right? Okay, cool. Imagine now, that's back to my example, A invokes a function foo from B and passes O2 as a reference, right? Well, like it's like passing a buffer. So what's wrong? Now, obviously, B can access this subtree, right? Because it has a pointer to O2. Okay, so far so good. But what happens if B crashes? Essentially, there is a bug in B and it panics here. I wanted to say panic. What really happens? Like the question, can we clean up any state? Well, you say, look, why not? Like typically, it's if languages support something what is called thread unwinding. It's like if you see in C++, usually that's in Java, that's how you catch exceptions, right? So you say, look, I got a bug somewhere like later in my stack frame, but I can unwind and clearly return just an error to the caller. That's okay, right? That's not bad. But what really happens to those objects? Because what if B left those objects which it could reach in some inconsistent state? Because it can, maybe it acquired a spin lock and was updating objects O3 or 2 or 3 or 4, sorry, and then suddenly crashed. And maybe they are still under a spin lock, and maybe the lock is actually inside the O2, and like A, which will try to access O2, will get a deadlock and will never be able to access the state of which got returned like from B as an error, as part of the error, right? So you see the problem. So if you allow uncontrolled sharing of state, you quickly end up in a situation in which you really might have some state which is broken in case there is an error somewhere in a system. It's somewhat similar to this idea which I was trying to explain on Monday, where I was saying, look, even if you take device drivers in a Linux kernel, you take them out and you isolate them, you run them in isolation, they still semantically share a lot of state with the kernel, meaning they pass the pointers into the kernel follows the registration protocol, like maybe has some callbacks. And if this thing crashes, then the kernel cannot really proceed forward because it says, okay, I have some dangling pointers. I don't really want to know what to do. I opened the driver, but it just crashed. Like I want to close it, but what am I doing with all my data structures which are allocated to handle this driver? How to do the cleanup? What if some locks are held? So it's a big problem. And in these language systems, it's kind of like becomes even more apparent, because apparently, like typically in a kernel, you just share like simple buffers, but here, kind of like the nature of the language kind of pushes you forward to share not just individual objects, not just plain buffers, but really like complicated data structures, like semantically complex recursive data structures, like lists, trees, vectors, stuff like that, right? Okay, so that's bad. Similarly, there is like another problem. How can we clean up B? meaning that what if like as part of this invocation, while running before crashing here, B actually added a pointer from 04 to 06. Like maybe that's what expected. Maybe it has to add like a list of objects, which means something, right? Like if it's a web browser, you can imagine it's a DOM tree, something like that. The question like, can we deallocate state of B? Not really, because we don't really know, because maybe this state is now reachable from A. And if you just simply delete all these objects by just somehow deallocating them, then, you know, this pointer becomes invalid and dangling, and A will crash later, right? So that's another interesting observation. So it's not trivial to solve this. So, however, what people were making, the observation which people were making over the years is that they came to the conclusion that the main problem is this uncontrolled sharing of state. And if you can eliminate shared state, you probably can come up with the ways to clean up the state of those isolated subsystems. And again, like despite the fact that I'm talking about a safe, I call the lecture Safe Operating Systems, operating systems implemented in safe language. And despite the fact that I'm talking about them right now, the same problem applies to regular hardware-based isolated kernels. Like if you think about it, the moment the state starts propagating between the subsystems, or like in a distributed system, for example, between servers, it's very hard to recover from a crash of one of them, right? Okay, so the key insight in those language-based systems, in the recent generation of those systems, is that we will try to avoid or try to eliminate the shared state completely. Meaning that, well, if you have this like two subsystems A and B, they by default don't share any state. And if you want to pass a pointer to O2 here, for example, from A to B, we're going to move it, meaning that A guaranteed to lose this access, right? So this reference will become invalid, similar to how it's done in Rust, right? Which means that all this object hierarchy will suddenly, atomically, upon function invocation, will start belonging to B, right? If we do this, what it means, if we pass this green pointer to O2, A doesn't have access to O2 and any objects which are reachable through O2, meaning that there cannot be a pointer like this. This is not allowed either, because that would be unfair, right? So you really you have to be careful. You have to make sure that somehow this discipline is enforced, right? And if we adopt this move semantics, like again, I keep talking about move semantics, but now it's like you kind of like we made a circle. Like I used it in hardware-based isolation systems to protect against times of check time of use attacks. But here it's like to eliminate the shared state, and the same applies there. So there it also used to eliminate shared state. So if you pass those objects, there will never be a case where there's a state shared between A and B, right? It's hard to like immediately understand, but this is essentially like, this is what it is, right? Okay, so if we do this, then how does it work? If we suddenly crash inside B here, we return to an error to A, but however, we will never return anything back. And like all these objects which somehow belong to B can be cleanly deallocated, right? So essentially it's called isolate a fault, meaning that like isolation of faults. If there is a fault in B, we can somehow cleanly return to A, making sure that A can keep running, or the system can move forward, or maybe even can try to recover B somehow. But like essentially that A is not contaminated by B state, or is not contaminated by any shared state, right? And all these objects essentially, which we like what I was saying, like I mark them red, we can deallocate it and essentially like like remove from the system and reuse the same memory, because we know maybe B allocated a bunch of stuff on a heap, and like now it crashed, so we just want to reclaim this memory because B is in some inconsistent state. We don't want to keep it allocated, right? Okay, so hopefully this is clear, but because there is a couple of challenges, right? So first of all is how to enforce this move semantics, right? Because again, in a general safe programming language, like it's typically not guaranteed, right? So like essentially nothing prevents you from having this pointer from 05 to 04. And even if you pass this pointer across pointer to 02, like A still can have a pointer to this object hierarchy, right? And in the past, people did different like approaches. One possible approach is do a deep copy. So essentially when you passing it across, instead of like passing this hierarchy, you just create a shadow copy. Like I say shadow, but you just like you copy the objects one by one. So and like literally people were doing it. And like if you have forgot what I was trying to say, but essentially yes, if the object hierarchy is deep, obviously it's non-trivial performance overhead, right? But people were doing it. There's also this idea that we can mediate all object accesses. And this idea was enforced in jkernel, and essentially like this, despite the fact that 05 might retain a reference, 05 will not be allowed to use it. So essentially like at the point of dereferencing, we can trigger a check and say, look, oh, no, you cannot access this object anymore because it was moved to some other subsystem. That which means that it instead of doing a deep copy, you just have to update a specific flag on each object. So it's not ideal either, but okay, people try to do that. But really, like when this idea came to like in a full power, it was when the Singularity operating system was built by Microsoft Research. They took a C# subset of C#, which they called Zing sharp for Singularity sharp, and used static analysis to essentially enforce the fact that if you invoke a function across an isolation boundary, the move semantic is actually enforced, like not enforced, but like your code essentially kind of like follows the move semantics. That was fine. That's essentially this idea later on inspired kind of Rust, I was saying, right? But like it wasn't super clean because the language itself was not linear. You can have multiple references on your heap, right? So this is allowed, like essentially, like this object has two references, but like only when you pass objects across, the Singularity was enforcing the invariant that, objects on a special exchange heap follow this linearity and they will be moved across subsystems, right? So still a huge step forward, but still required a complex verifier, and sometimes even I think they needed some dynamic checks in some corner cases, although recently I was trying to recover this knowledge and like look through the papers to really understand when. I wasn't able to find it, but I think they did. But really, of course, like in Rust, this check can come for free. That's the beauty of Rust. Remember, I said that this linearity or single ownership has deeper consequences than just safety. So one of these consequences, which I promised we're going to see today, is that, Rust is linear. So it guarantees that there is only one pointer. There is no pointer like that. This is not allowed in safe Rust, right? Because that's non-linear. So this like variable has two owners, 02 and 05. That's not allowed in Rust. And like by default, Rust is a linear language. So it essentially, if you pass a pointer across, you're moving it or borrowing, maybe immutably, right? Rust allows borrowing, but really it's just moving. So in Rust, this move semantics comes for free. This is beautiful because if you say, look, I want to build my safe operating system in Rust, it's immediately like this problem is just taken care for. So that's great. Okay. Unfortunately, there's this like still a little bit of complication, right? We said that Rust doesn't have a garbage collector. So, and there is a crash inside B. Rust doesn't provide a mechanism to say, look, I will trivially deallocate all the objects which were reachable from, I don't know, from some root variable in B, right? There is no such mechanism. So you need to somehow track which objects are owned by B and then somehow deallocate the state. So you have to be careful. So when you build this, like when I was using my, like, sorry, I wanted to switch here. When I was just programming here, I was just freely saying, okay, I'm sorry. Oh man, like everything is on the screen. I was saying like, okay, guys, we just program in a language, no problems. But this is kind of the issue which we have to address. We have to make sure that like we track which process owns what, right? And I will come back to it in a second. Okay, cool. And of course, there's another like interesting problem that if you have cycles in Rust, first of all, can you even have cycles in safe Rust? You cannot, but Rust provides you some unsafe extensions. So if you choose to have some unsafe extensions which you trust, then still it's a little tricky to deallocate cyclic objects. It's probably possible by carefully walking the graph, but that's not fun, right? So you might choose to either go with cycles and come up with some mechanism to figure out how to deallocate objects like cyclic data structures, but ideally better maybe not. Maybe forget about cycles. Maybe some objects which we pass across will never have cycles. Maybe it's easier. So, and this is what we essentially doing in this operating system which we built, Redleaf. So we set back to this special heap construction, right? There will be a special exchange heap. And objects on the exchange heaps, they're special because those private objects which live on private heaps, they can do like whatever they want, right? So they might even have bits of unsafe Rust. If there are some extensions which we trust, kind of like reference counting, whatnot, right? But those are special. And exchange heap is for the objects which we can pass across. It's very similar to Singularity. It was doing the same, just we do the same. And there will be a couple of rules about this special heap. So first of all, the cycles are not allowed because we want to be proactive and make sure that when we know that, for example, subsystem B owns this reference and owns an object 07 on a shared heap, we will call a custom drop method and just essentially deallocate everything what follows like 08, but there will be no cycles. We probably can support cycles, but we said, okay, no, we don't want to do this. So no cycles on data on the shared heap. As I said, we can track ownership, like we can deallocate the data structures without leaks. But on a private heap here, we allow cycles, right? So any data structure. So essentially, because I will show you how we're going to deallocate, like we're going to deallocate separately this heap and everything what is owned by B on a shared exchange heap. Because for this private heap, it's much easier. We'll just wipe it at once. So another rule which we enforce is there will be no references between domains. Essentially, one domain cannot have a reference here, right? This is not allowed. And also objects on the shared heap cannot have references back like this. Even if they are linear, this is also not allowed. That's kind of important because those two kinds of references are essentially prohibited. And what it gives us is that we know that objects on the private heap, they only can point to objects, either to the objects on a private heap itself, or to the objects on a shared heap, but we track the ownership here. So we can essentially just wipe out the entire private heap. Just simply deallocate the memory. Don't even call the destructor. So we know that like as long as this heap comes from a private memory allocator, and we say, look, all the memory, like in Rust, in order to allocate something on a heap, you use something what is called a box. Think of it as a new operator, but every time you invoke new, you essentially go to the memory allocator, like a slab allocator, and gets a like 64 bytes of memory, for example. And we keep track that whatever this slab was allocating was used for B. And if we wipe all this memory, return it back to the allocator, it's safe because like there is no pollution, because there will be no reference like that, because this is not allowed. There will be no reference like that, right? Because this is also not allowed. So if all of this heap is disappearing, it's safe because there will be never be a dangling dereference. So it's kind of like temporal safety is enforced, right? Okay, cool. And now the question like, okay, if we have this special heap construction, can we really build an operating system out of it? And the answer is yes. So it's kind of like back to my example, but it's pretty much the same. So because I was explaining kind of this Redleaf. So the way we build it is the following. So we say we have a small microkernel, which boots on like stock x86 server or desktop hardware, supports multiple CPUs. And it's very minimal. So it's only supports like mechanisms to create user domains, like essentially processes, or like those processes, we call them domains. It supports threads and scheduling, kind of like x86 context switches and timer interrupts and stuff like that. So we have interrupt dispatch, and it has a coarse-grained memory management. That meaning that it does have like it essentially can allocate memory to the domains in the granularity of individual pages or larger, right? So no small objects. I will explain why it's important in a second. So, okay, everything else in this system executes as a collection of language isolated domains, right? And the boundaries are enforced through language safety. So everything runs in ring 0. So like from here, to here, it's all ring 0, right? Okay, so essentially, okay, we want to run device drivers, we run them as isolated subsystems. We want to run some kind of operating system, like we call it RV6 for Rust version 6, meaning it's like xv6 but written in Rust, but essentially it has like a file system and a network stack and maybe some core kernel. It's all of these are language-based domains. I will explain what these proxies are later, but they kind of like allow us to recover domains. But essentially, that's just how it works. And if you have like RV6 might have user-level domains as well. They run again like on top of this the whole construction. Like if you have something like a shell or a cat or WC, it will run as a process or as a domain on top of RV6 core kernel. Device drivers may also be like inside user domains, so kind of like DPDK style. Like what we do here is essentially we say, look, this process, like instead of being a x86 process, it will be just talking to the device driver directly. It's allowed in our system. Why not? It like allows us to like run a little faster. And of course, all communication between domains goes through this shared exchange heap, right? So essentially, if you have a pointer, you just kind of like have it there on the shared exchange heap, according to the rules how I explain them, right? Like again, just emphasizing one more time, everything runs in ring 0, right? No hardware isolation, no SFI, just language-based isolation, right? We trust the language to implement like rules of the language correctly, meaning that there is no like some kind of a weird operation which allows you to access any object in the system, kind of like figure out a pointer which points from a user process, directly to like some kind of a object in a kernel. Like this is not allowed, right? But it's at the level of the language. Those again, like remember I mentioned that we build programs as regular L files. They have a data and a text sections, like everything similar to regular kind of programs which you would expect in x86. They are all regular Rust code. However, we disallow essentially unsafe extensions. So mostly it's only safe Rust. And we have a small allow list, white list of libraries which we trust. Really small one, because like, for example, we trust a vector. Vector internally has unsafe code. We do trust it, unfortunately, in this system. So which is like a disadvantage, but it's okay for now, but later on it may be fully verified, and then we can trust unsafe code as well, making sure that it just doesn't have a bug. We also rely on this trusted compilation environment, which essentially makes sure that we compile in a specific compiler with a specific optimization, not optimization, but with specific settings to make sure that ABI at the level of the ABI safety is preserved, right? And then essentially the microkernel has a method which says, okay, domain create, I take an ELF and I will just essentially go inside the microkernel, do the integrity check, meaning that I will check the signature, that it comes from a trusted compilation environment, and then essentially just use an ELF loader to create a domain which starts running the code as a user process on top of this microkernel, right? Okay, cool. So this is nice. Then all these private heaps are essentially sitting there inside the process. The microkernel has its own private heap. Each domain has private heap, private data, per CPU data, stuff like that, right? So this is like very much like a process in x86, right? If you think about it, it has a main, we passed a pointer to syscall, so it can go back into the kernel, but then plus some other arguments as well. But really, it's just more or less encapsulated and cannot escape. Remember our goal to make sure that, if there is a private heap, we have a guarantee that there are no pointers to other domains or no pointers to like shared exchange heap. But our goal is to essentially wipe this heap completely, as I said. So what we do here is that we say, look, we will use a two-level allocator scheme. So internally, each process will run a slab allocator, which can essentially, remember slab, it can manufacture, like allocate fine-grained objects like 32 bytes, 64 bytes, 128 bytes. And that's needed to support the box operator, which allocates memory in Rust, right? So you can write normal Rust, but similar to how user-level allocators in x86 are working, the slab allocator, when it's need additional pages, instead of using set bracket system call, they just said, okay, give me a page or give me like a couple of pages. And that's what we essentially support. So like this second level coarse grain allocator, which microkernel is implementing, is essentially body. It's like kind of what we discussed in the first part of this class. That's why like those kind of allocators are coming back. We re-implemented them in Rust, but they are like essentially the same as we saw in case of a Linux kernel. And what we do is that every time we allocate a page, we keep a record. So essentially we track all the pages which we allocated for this specific domain. And essentially when there is a bug here, if it's a bug, it's a bug. Looks like a bug. Okay, bug. Then we just essentially can walk through all these pages and essentially just say deallocate them. And this is how we deallocate this entire private heap, right? To implement exchange heap, we remember there are those rules which we have to follow. So essentially we say, look, I'll go over them again. So we implement a special type, rref, or remote reference, which take a type here as an argument. So it allocates T on the shared exchange heap. So it's very similar to how we allocate box of T, so essentially allocate something on the local private heap here with a box operator. We use the same operator here. Rref allocates essentially an object on the shared heap. This rref is a little special, so it essentially contains the ID of the current domain, which owns the reference. It contains how many times it was borrowed, because we support borrowing of references across domains, and a pointer to an actual value of T on this shared heap, right? So that's kind of like to track who owns it and like when it's time to deallocate it. And what we do is that every time like we allocate something on a shared heap, we maintain a data structure in the microkernel, which we call a heap registry. And this heap registry tracks all rrefs in the system. So essentially, if there is an rref on a shared heap here, it will be in this registry, and we know that it's there. And why we need it is that essentially when a subsystem crashes, we just do a linear scan of the heap registry and deallocate all the remote references which are owned by the crashing subsystem, right? So that's how we deallocate all the state on the exchange heap, right? Because this heap we can just blindly deallocate at the level of pages, but this we really have to like follow, invoke destructors, because these pointers can point to other RFs and stuff like that. So it cannot be done like blindly, because this shared heap is like a collection of objects owned by different domains, right? Okay, so there's a couple of rules. So RFs on a heap, like the question, like remember, we need to enforce the rules that there are no pointers like that. If there is a ref pointing to another ref on a heap, which we allow, there we don't allow cycles, right? Because then if we have a cycle, we cannot really deallocate easily the object, right? So okay, cool. So what we do, we allow that refs can point to other refs on the exchange heap, but we implement something what we call this heap isolation invariance, right? Invariant number one, there will be no cycles on the exchange heap. I just talked about it. Invariant number two, no pointers from the exchange heap back into the private domain heaps. And invariant three, no pointers between private domain heaps, right? Essentially, there's three invariants. The question is like how to implement them in a safe language. Because if you just blindly allow having some pointers here in these data structures, which we allocate on a shared heap, then you can easily allow those pointers to point into the private heaps, right? Because like the goal as a developer, like when we build the system, we say, look, you really can put any type T on the shared heap. This type T can have a reference, maybe, but if it's a reference, it can only be an RF which points to the object on the shared heap, and plus there will be no cycle. So this is linear. It's a little harder to build than immediately than a trivial solution. Essentially, what we do here, we control all the types which can be allocated on the exchange heap, and the types which can be passed in a cross subsystem invocations. Like for example, you pass a foo. Obviously, somehow we say that foo can only take a pointer to the exchange heap. It cannot take a pointer which points back to the caller domain, right? Because then that immediately breaks an invariant. So we enforce those invariants at the level of a type system. So essentially, we say, look, we'll create a special type system, which allows us to catch those cases where whoever develops the domain, we don't control, like there's no like a user, like a human being who essentially looks at this code and just says, okay, look, I claim that like all the invariants are preserved. So we trust the file system. We trust the type system to do this. We introduce this idea of exchangeable types. There's the objects which can be exchanged across domains and allocated on the shared heap. So exchangeable types can be RFs themselves, obviously, a subset of Rust copy types, something like U32, U64, because those are not pointers. But for example, in Rust, a pointer to a function or a pointer to a closure can be copied, right? So those we don't allow. So we rule those out because like the closure, if you allow a pointer to a closure, then the pointer can point like back, for example, into this domain where the closure is allocated. And of course, if this subsystem dies, then, this pointer is dangling. Similar for a function, right? If you allow a function pointer to point back to the domain, then it can like lead to an unsafe situation. And any composite types which are constructed of exchangeable types are kind of like tuples, arrays, enums, structs, stuff like that. We allow references to traits, which means that one domain can introduce a pointer to a trait, meaning that it's kind of like a pointer to an interface which domain exposes, right? And however, all methods of those traits can only be like restricted to exchangeable types, meaning that even if you pass a pointer to an interface, the interface is recursively validated that it will only allow exchange of exchangeable types. So you cannot like send a row pointer across, right? That's kind of like, that's a big invariant, right? And it turns out that is impossible to do at the level of the Rust type system itself. It's just not sufficiently expressive. So what we do instead, we essentially create, again, an interface definition language compiler, which validates that types that can be allocated on the heap follow the rules of exchangeable types, right? So essentially, it's a little hard to explain. So here's an example. So imagine we have a trade, which is an interface of a block device, which implements a Rust like in Rust it implements an interface. So we say, look, those interfaces, they can take and return exchangeable types. So OP types like U32, arrafs, that's fine. They also either move the type or borrow immutably. So we don't allow the mutable borrow, but allow the immutable borrow, because it means that in case of an immutable borrow, the caller still owns the object, right? So if the callee crashes, we can still we do not deallocate the object. We just return back to a caller, and then caller has it back. And they also we introduce a specific constraint that all the functions return an enumerated type RPC result. So it's either the object which we care or the error, right? So for example, here it can return either an error or none here, right? Okay, cool. And essentially, I mean, it allows us to cleanly catch all errors between the domains. So those exchangeable types allow us to essentially move references to the shared heap across the subsystems, right? We also introduce the abstraction of a proxy. So proxy is the part of the trusted computing base, and the main role of the proxy, to essentially, if B crashes and A still has a pointer to a trade inside B, it will not immediately point to the B itself, but it will be wrapped by a proxy, which means that if B crashes, it will still retain a pointer to a proxy. So we do not deallocate proxies, right? And instead of doing an unsafe memory access, the proxy just checks the liveness of B and says, okay, if B is not alive, I'll just immediately return an error, right? And proxies are automatically generated by the IDL compiler from other domain interfaces. So it's essentially not a human written code. So essentially, if you have a trade definition like this, our compiler will take it, check that all the types are exchangeable types, and create a code to make sure that the proxy can wrap this interface. And when the trade is passed across, it will be wrapped with a proxy. So this idea of wrapping with a proxy comes from object capability languages, but it's kind of neat. We also have support for recursive arrafs. Remember that each arraf has an owner, but only the root of the hierarchy is moved, essentially between domains. So the children in the hierarchy has this specific symbol, which is called the bottom, which means that this arraf is not owned by a domain, it's owned by another arraf, which means that when we move an object on a cross subsystem invocation, we only have to update the ownership of the root object from A to B. That allows us to avoid walking the entire hierarchy of objects. So for example, if you're passing a complex object hierarchy with thousands of objects, again, the DOM tree, right? And all of these objects will have a simple bottom saying that, okay, there are all owned by some other references, and only this one will be owned by A. And on a cross subsystem invocation, sorry, trying to write A, it will be moved from A to B. It's a true kind of zero copy mechanism, kind of like we saw in this hardware isolated systems, right? So essentially only this one field gets updated. You don't have to walk any of this object hierarchy. And that allows us to essentially implement this cleanup. So when domain crashes, we collect the heap, essentially take away, like deallocate the private heap. We walk the heap registry here and essentially call the drop method for each araf on the heap, right? Making sure that, everything what was owned by this subsystem on a shared heap is deallocated. The proxy stays alive. So if then like A tries to invoke B again, instead of going inside B because this memory doesn't exist anymore, the proxy immediately returns an error saying, okay, by the way, B is dead. So here's an error. And that's nice. So essentially, we were like fighting a little bit with implementing like custom drop method, stuff like that. But essentially, we built this system which implements this fault isolation. So I might talk a little bit more about it on Monday, but right now I ran out of time, so I would like to stop here. It's already 1 hour, 20 minutes. So you guys are probably also tired because it's probably was very dense, and because like again, I didn't stop for any questions or anything. So, but nevertheless, so the conclusion here is that arguably this language-based isolation has a future. I cannot say that it solves all the problems immediately, just because we have those unsafe language extensions and it has a large trusted computing base of a language. So essentially you trust the language to implement all the types correctly, everything like that. You need a trusted compilation environment. So that's not fun. But on the other hand, it's very fast, and we should come back on Monday and talk about essentially the performance of those systems, like how much overhead is introduced by Rust and how much overhead is introduced by those cross-domain invocations, which are almost like function calls, but not really, but close. But maybe that's one possible future for where the operating systems will go. So let me stop here, and I will then see you all on Monday in person. See you. Have a good Thanksgiving.